Swayam Prabha. Digital India. Educated India.
Welcome friends to this last lecture of week 12 or module 12 of this NPTEL online certification course of environmental soil chemistry, and in this week we are talking about different analytical methods for measurement of soil pollution. And in this last lecture we will be talking about some methods for inorganic pollutants, and also we will be talking about the analytical methods for major organic pollutants. So, in the last lecture we are talking about the working principle of atomic absorption spectroscopy, and I showed you the schematic diagram of the atomic absorption spectrometer, and then we talked about the hollow cathode lamp. So, this is the picture of the hollow cathode lamp. You can see here it has different components. It has a quartz window, it has an anode ring, and there is an insulation disc and cathode also present there, and also there is a plug. So, the cathode is the hollow cathode lamp of a particular element. The cathode is made up of that particular element. So, and this why we use the hollow cathode lamp? We use the hollow cathode lamp because the requirement for a source of narrow lines of the correct frequency. And this hollow cathode lamp is basically filled with, why we call it hollow? Because it is filled with argon or neon, which are inert gases at a pressure of 130 to 170 Pascal or 1 to 5 torr. So, this is how we call it hollow cathode lamp. Now, the cathode at this hollow cathode lamp, as I told you, is contains the elements being analyzed. So, therefore, the atomic radiation emitted by the HCl or hollow cathode lamp has the same frequency as that absorbed by the analyte atoms in the flame or furnace. So, basically it says that since the cathode of a hollow cathode lamp is made of a particular element which is suitable for measurement of a particular element, therefore, the atomic radiation which is produced by this hollow cathode lamp or emitted by this hollow cathode lamp has the same frequency which will be absorbed by that element under consideration, which is in the flame or furnace. Now, the line width from this hollow cathode lamp is relatively narrow, which is compared to the line width of atoms in the flame or furnace, because of the low pressure in lamp and lower temperature in the lamp, that is creating less Doppler broadening. So, the line width from the HCl is monochromatic versus the sample. So, basically that is why I am telling you we are producing the monochromatic radiation, which has the wavelength which is perfectly coincide with the wavelength which is being absorbed by the particular element, or it is basically the same wavelength. So, different lamps are required for each element, although some are multi elements. So, this is a characteristic feature of this AS, that you need to use individual hollow cathode lamp for individual element. Okay. So, now we have covered the AS. Another important instruments which we are going to talk about, this is called the ICP-MS. Now, you know what is ICP, that is inductively coupled argon plasma. So, basically it is the same. So, the ICP-MS is a type of mass spectrometry that uses an inductively coupled plasma to ionize the samples. And this is a very precise and very sophisticated instrument, and this instrument is basically used by the laboratories as a gold standard for measurement of different elements. So, this can measure a wide range of elements, and the precision level is quite accurate, and also the level of detection or limit of detection is very low. we can go up to ppb to ppt level sometimes. So, the basic principle is it has a ICP inductively coupled plasma for ionizing the sample, which is attached to a mass spectrometer for measurement of those individual ions. So, one of the major benefit of this instrument is it can sample the analyte continuously without any interruption. Now, mass spectrometry, what is the benefit? You have already seen ICP AES, atomic emission spectroscopy. Now, we are talking about ICP MS, which is more sophisticated. What is the, what is it? You can ask me. Now, mass spectrometry, remember this MS stands for the mass spectrometry. Now, mass spectrometry is basically used to provide the information about the elemental composition of the sample of matter and the structure of the inorganic, organic and biological molecules, and the qualitative and quantitative composition of the complex mixture often occurs by fragmentation part of the molecular ions to produce the ions at lower masses. So, you can see it has a wide range of application. If you want to go to the more detailed level, you have to go with this ICP MS. Now, remember that in this ICP MS, the ICP part helps in the proper ionization of the samples, and in these ions are dispersed in the mass analyzer when it goes, as you can see this is the ion source. So, sampling interface is there. So, this is an ICP. So, when this ICP from this ICP the ions goes to the mass spectrometer, these ions are dispersed in the mass analyzer based on their mass to charge ratio. We denote by this m by z or m by z. So, based on these their dispersion according to their mass to charge ratio, they are being separated and further they are being detected. So, that is why ICP MS is more sophisticated. If you want to go for measurement of a particular species of ion, for example, if you want to measure the harmful species of arsenic in the soil or water, like arsenic 3 plus or arsenic 5 plus, you have to go with this ICP MS. Now, what are the benefits of ICP MS? The benefits of ICP MS is, first, it has wide elemental coverage. It can measure a wide range of elements. I will show you in the next slide. It has extremely low detection limits. It can go up to PPT or ppm or sometime to, or basically nanogram to per liter to milligram per liter. So, you can see it can go up to parts per trillion level also. So, it has fast analysis time, all elements at once, and simple spectra. The spectra is simple, high throughput and productivity. It can measure a wide range of elements in a single go, and it can give you the isotopic information also. So, you can see these are the benefits of using the ICP MS. Now, there are certain technology, advancement of these different types of analytical techniques nowadays also help for development of different hyphenated techniques. What are these hyphenated techniques? Now, with the advent of commercialization of the ICP MS, hyphenated techniques coupling high performance liquid chromatography and gas chromatography are routinely used to separate and quantify the metalloid species such as those formed by arsenic, selenium and mercury. As you can see here, these are hyphenated techniques where we are basically combining these HPLC system to a ICP MS system. So, we call it HPLC ICP MS. So, basically these type of things will be useful for separating and quantify metalloid species for their specific and their analysis, like metalloids like arsenic, selenium, mercury. As you can see here, the mercury species are measured through these hyphenated techniques. So, sometimes instead of HPLC, we are also attaching the gas chromatography. So, GC-ICP MS. So, these are hyphenated techniques that used for more advanced and more sophisticated analysis and more accurate analysis of the desired species which are creating the pollution in the soil. So, this chart shows the different elements which are being measured by this ICP-MS, and you can see the detection limit range. You can see that these light blue are basically showing less than 0.1 to 1 ppt. So, you can see these are high, these elements can be measured if they are present in very less quantity in the soil. So, 1 to 10 ppt, then 10 to 100 ppt, 0.1 to 1 ppb, 1 to 10 ppb. So, you can see the detection limit for this instrument is exceptional, and very few instruments can match with this level of detection limit. So, this is why ICP-MS is widely used for these different types of analytical laboratories, and also different types of environmental pollution analysis projects. Now, regarding the total elemental analysis, let us talk about another important spectroscopic method, that is called X-ray fluorescence spectroscopy or XRF. Now, before going to the XRF, let us little bit talk about the X-ray radiation. Now, you know that X radiation, or composed of X-rays, is a form of electromagnetic radiation, and these X-rays were accidentally invented by the scientist Ronsen, and you can see here this is the first ray of his X-ray of X-ray of his wedding ring which he took, and so it was accidentally invented, and these X-rays have wavelength range from 0.01 to 10 nanometer, and it has the energy range from 0.125 kilo electron volt to 125 kilo electron volt. So, wide range, and the wavelengths are shorter than those of UV rays and longer than those of gamma rays. So, this is about the X-ray. Now, if you see the electromagnetic radiation and different types of X-rays, so these are the gamma rays, and you can see X-rays and ultraviolet rays, and after that this portion is a visible light, and from there we are getting the infrared, microwave, radio wave, extra-low frequency, and so on and so forth. So, these ultraviolet X-rays and gamma rays comes under this high energy radiation, and then infrared, microwaves goes towards the low energy radiation. Now, different types of X-rays are there. We can see after the gamma rays, you can see the next we get the hard X-rays, and hard X-rays you can frequently see in the airport security scanners. So, airport security scanners use the hard X-rays which are having the higher energy, and the soft, and also the relatively low energy X-rays are used for medical computerized tomography, mammography, and X-ray crystallography. So, hard X-rays are basically used for airport security, whereas comparatively lower hardness the X-rays which are having showing the lower hardness are used for medical chromatography, medical computerized tomography, and then mammography and X-ray crystallography, as you can see in this picture. Now, this X-ray fluorescence phenomena, what is X-ray fluorescence phenomena? Now, if we incident an X-ray from a source, let us consider there is an X-ray source. Now, in this X-ray source, if we generate this X-ray, and this X-ray basically goes towards an atom and ejects a shell ejects an electrons from the inner shell, there will be a void, and as a result of this void, the outer shell electron fills this vacancy. So, there will be a vacancy when these inner shell electrons will go up, and this vacancy will be filled up by this outer shell. And you know that there are different shells like K shells, L shell, M shell, and so on and so forth. And when this outer shell electron fills the vacancy, there is a energy difference, because when it moves from higher energy levels to the lower ground state, they will release some energy. So, this energy difference escapes as an X-ray with energy characteristics to the specific atom. So, uh, this is the phenomena of X-ray fluorescence. So, basically we are basically pointing an X-ray to eject inertial electrons. These electrons, when they are ejecting from the ground state, it is producing a vacancy, and this vacancy is filled up by the outer shell electrons. When it is coming to fill the vacancy, it is it is releasing some energy in the form of fluorescence, and that is the principle of X-ray fluorescence. So, you can see there are different types of orbitals like K, L, M, N, O and P, and depending on from where these outer shell electrons is moving, we have different types of peaks are named. For example, if some outer shell electrons are falls to K line, falls to this K shell, then we call it a K line, and if they falls from L to K, then we call it K alpha. If they fall from M to K, then we call it K beta, and so on so forth, and M line series is very weak. So, this is basically the direct excitation method. You can see here there is an X-ray source which are producing these rays to the samples, and this fluorescence is being basically detected by a detector which is basically further operated by electronics and the computer. So, this is how this XRF phenomena basically operates, and this is the, you can see that K alpha line and K beta line of iron. Just for an example, there are different types of X-ray fluorescence spectroscopy, three types mainly. One is called the energy dispersive X-ray fluorescence, the second one is called the WD-XRF, that is wavelength dispersive X-ray fluorescence, and the third one is called polarized ED-XRF. So, we do not have enough time to discuss all this, but these are very sophisticated and very accurate method for total elemental analysis. Now, what are the elements which we can measure through this XRF spectroscopy? Now, if you consider the ED-XRF, obviously this is a periodic table. You can see the ED-XRF can measure the elements from sodium to uranium. So, you can see a wide range of elements it can measure. However, this WD-XRF has wider range of application. It can measure from carbon to uranium. So, obviously wavelength dispersive XRF is more sophisticated and more costly than ED-XRF. So, this is an example, this is a picture of this ED-XRF, benchtop ED-XRF, and nowadays scientists have developed these handheld ED-XRF instruments. We call it portable XRF or PXRF. So, these are called the portable XRF or PXRF instruments, which they basically using the same ED-XRF principle, but they are portable in nature. So, this portable ED-XRF spectroscopy or portable X-ray fluorescence spectrometer, basically this is the construction. So, there is an X-ray source which generates the X-rays which ejects the electron, and when the outer shell electrons goes to fill up the vacancy, it will release the fluorescence which are being detected, and this signal digital signal processor is there. Ultimately, it goes to the CPU or central processing unit, which basically store it and or it transmit it through wireless. So, this is basically the working principle of not only working, this is the working principle of portable XRF. This is an example of portable XRF from Olympus. There are several companies which develop this instrument. These are very portable technology, and they are very easy to use. They are operated through batteries. You can literally carry it in any field and you can measure the elemental concentration directly in the field. So, why XRF is so popular? There are several ways, there are several reasons the XRF is popular. First of all, it helps us for elemental analysis. It is fast, the handle XRF can give you the results of total elemental concentration in only 60 to 90 seconds. It requires minimum sample preparation. It can deal with the powdery samples like soil. It can deal with the liquid samples also. Now, non-destructive in nature, it is flexible, it can analyze the solids, liquids and powders. It is very precise, it has got low cost of analysis, and non-technical operators, it can be operated by both experts and non-technical operators, and it is simple to operate. You can see here the scientists are using directly this handle XRF or handle EDXRF in the field for measurement of elemental concentration in the soil. So, instead of bringing the samples into the lab and going for the cumbersome methods, you can directly go to the field and you can directly measure the elemental concentration in the field itself. Now, we have covered these organic pesticide, inorganic pollutants. Let us focus on this organic pollutants and what are the methods. So, let us start with the pesticides. Remember that in the field experiments, soil solution can be recovered with the inert porous cup or lysimeter equipments, which will help us for these pesticide residue analysis in the field. And in the laboratory, among the laboratory techniques, water extraction by pressure or centrifugation is basically used to extract the pesticide residue. And also remember that mixtures with non-polar solvents are also used with the most lipophilic pesticides. Now, what are the analytical methods for pesticide analysis? The most important analytical methods used for the pesticide analysis is gas chromatographic method. Now, this gas chromatographic method can detect less than 1 ppm of with certain detectors. It has got different types of detectors like TCD detector, like ECD detector, like FID detector, we will discuss. Now, this gas chromatography can detect less than 1 ppm with certain detectors, and it can be easily automated for injection and data analysis, and which has been used for measurement of different pesticides like organophosphorus and triazine, etc. So, let us see the principle of gas chromatography. Now, this shows the schematic of of the different parts or different components of the gas chromatography. So, in the gas chromatography, mobile phase is a gas and the components are separated as vapors. So, it is thus used to separate and detect small molecular weight compounds in the gaseous phase. The sample is either a gas or a liquid that is vaporized in the injection port. So, you can see there is a carrier gas which used to carry the sample. So, sample could be either gas or liquid, which are basically introduced through this injection port, and the mobile phase for this gas chromatography is this carrier gas, which we have already told. Typically, it is a helium because of its low molecular weight and being chemically inert. So, this pressure is applied and the mobile phase moves. So, this mobile phase basically moves through these columns with the sample, and the separation is accomplished using a column coated with the stationary phase. So, these columns are basically coated with the stationary phase. So, we are injecting the sample, we are flowing this carrier gas or the mobile phase, which is basically helium. So, this helium mixed with the sample is moving through the column, and this column is basically coated with the stationary phase, and based on the interaction of the sample with the stationary phase, it will be detected, and ultimately we will be seeing different peaks of different components of this of our analyte. Now, the equilibrium for gas chromatography is partitioning, and the components of the sample will partition or distribute between the two phases, that is stationary phase and mobile phase. So, this this sample, when we are moving through this mobile phase through this stationary phase, which is present in this column, these samples will differentiate themselves, they will separate out. So, compounds that have a greater affinity for the stationary phase will spend more time in the column, and thus they will elute later and have a longer retention time, and based on this retention time we will get different peaks, as you can see in this picture. So, then longer retention time than the samples that have higher affinity for the mobile phase. So, those samples which have got higher affinity for the mobile phase will elute more easily as compared to those compounds which are having lower affinity. So, for the mobile phase and higher affinity for the stationary phase. So, the components which are having higher affinity for the stationary phase will be eluting later, and therefore, they will give the different peaks. So, based on this peak analysis you can get the idea about the different components of the analyte mixture. Now, in the gas usually we use the nitrogen or helium as the gas carrier gas. Sample injector is either syringe or septum, and columns are basically different types of tubings packed with a small uniform size, inert support coated with the thin film of non-volatile liquids. There are different types of detectors, either TCD detector or FID detector. TCD stands for the thermal conductivity detector and FID stands for the flame ionization detector. They are used for the specific purpose. So, this is gas chromatography. The second one is HPLC. HPLC stands for the high performance liquid chromatography. It is a kind of liquid chromatography, and it is a method which is widely used for wide range of pesticides. So, if you see the principle of HPLC, it is also same. So, basically the separation principle, based on the separation, chromatography is a separation based principle. So, you can see the separation principle of HPLC is based on the distribution of the analyte or the sample between a mobile phase, that is eluent, and the stationary phase, that is a packing material in the column. And so, basically you can see in this picture there is a sample which we are injecting in this injecting valve, and also there is an eluent which is a mobile phase. So, we are moving this eluent through a peristaltic pump through high pressure, and this eluent is moving with this sample through a column which is packed with a stationary phase. So, based on the sample interaction with the stationary phase, they will have either higher affinity to the stationary phase or lower affinity. So, based on that they will elute at different times, and therefore, they will be detected just like as gas chromatography. And so, basically the separation principle of HPLC is based on the distribution of the analyte or sample between a mobile phase, that is an eluent, and a stationary phase, that is packing materials of the column. Depending on the chemical structure of the analyte, the molecules are retarded while passing the molecules, and the molecules are retarded while passing the stationary phase, and the specific intermolecular interaction between the molecules of a sample and the packing material defines their time on the columns or retention time in the columns. Hence, different constituents of a sample are eluted at different times, thereby the separation of the sample ingredients is achieved. So, this is basically the working principle of HPLC. A detection unit is there, UV detector recognize these analytes after leaving the columns, and the signals are converted or recorded by a data management system and then shown in a chromatogram. Just like in case of GC we are getting a chromatogram, in case of HPLC we are also get the chromatogram. After passing the detector unit, the mobile phase can be subjected to additional detector unit, a fraction collection unit to the waste. In general, HPLC system contains the following modules. What are these? A solvent reservoir, as you can see it is an eluent reservoir, a pump, a injection valve, a column, a detector unit and a data processing unit. Now, the solvent eluent is delivered by this pump at high pressure and the constant speed through the system, and the analyte or sample is provided to the eluent by the injection valve, as we have already seen. Okay. Let us talk about the hydrocarbons. Now, in the hydrocarbons basically it is measured through FID detectors. So, this FID detector stands with the flame ionization detector. So, the sample is basically injected into the GC unit and it moves through the column to reach the flame ionization chamber. So, this is a flame ionization chamber, and this flame thereby give rise to flame ionization chamber thereby give rise to signal to the computer unit that generates chromatogram with peaks of individual molecular group. The operation of the FID is based on the detection of ions. So, this is an FID detector. So, this FID detector operation is based on the detection of ions formed during the combustion of organic compounds in a hydrogen flame. So, you can see this is a hydrogen flame. So, detection of ions formed during, so ion due to the flame there will be the formation of ions, and this flame is produced by the hydrogen gas, and the generation of these ions are proportional to the concentration of the organic species in the sample gas stream. So, this is how this GCFID basically works. Another instrument is there, that is called GCMS, which we use. So, basically it is another mass spectrometry attached to the GC system. So, the separate, this GCMS separates the chemical mixture and identifies the components at a molecular level, and remember that it is the most accurate tools for analyzing environmental sample, just like we have discussed in case of ICP-MS. GC works on the principle that a mixture will separate the individual substance when heated, and the heated gas are carried through the column with an inert gas such as helium, and as the separated substance emerges to the column opening, they flow into the mass spectrometry, and this mass spectrometry basically detects the different components of this gas mixture. So, this is how this GCMS basically works. So, this is the schematic of GCMS. You can see here there is a sample inlet, then GC column, ultimately it goes to the there is a transfer line, it goes to the ion source, and then it moves to the mass spectrometer and finally to the detector and control systems. So, this is the the schematic diagram of GCMS, which is a very sophisticated instruments. Analytical instruments for volatile organic compound, like these volatile organic compounds are the aromatic, they are both aromatic and chlorinated and have boiling points below 200 degree centigrade, are categorized as hazardous. There are different methods for analyzing them. They are carcinogenic. US CPA recommended methods are purge and trap followed by GCMS technique. Another technique is known as solid phase micro extraction or SPME, which is a technique that involves the use of a fiber coated with an extracting phase that can be liquid or polymer or a solid or sorbent, which extract different kinds of analytes, including both volatile and non-volatile from different kinds of media that can be liquid or gas phase. So, these volatile organic compounds are also being analyzed in different types of environmental chemistry laboratory for detecting the pollutants. And finally, we are going to talk about the analytical methods for humic substances. So, there are different types of solvents and reagents for extracting the humic substances like sodium hydroxide, sodium carbonate, sodium EDTA, dimethyl sulfoxide, formic acid, acetone, water, HCl mixture, and fractionation of the humic substances can be done by gel permeation chromatography or ultracentrifugation chromatography with this polyvinyl pyrrolidone at stationary phase, and isoelectric focusing is often used to characterize the humic material extracted from soil and other types of matrices. So, guys, this brings the end of this week lecture and end of this course. And in this lecture, we in this week we tried to cover as much as analytical methods as we can cover. However, remember that there are more methods, sophisticated methods, which are available in the environmental science domain. It is not possible for us to discuss all of them, but I would recommend you to please go through different advanced analytical chemistry books and see what are the advanced options for measurement of the environmental pollutants which are present in the soils. These are the references which I used for this module, and you can consult these sources for more comprehensive information of pollutant analytical methods for soil pollutant measurement. So, friends, we have completed almost this, we have wrapped up this course, and I would like to especially acknowledge the contribution from my two PhD students, Ms. Shweta RK and Ms. Swagata Mukhopadhyay, who helped me for developing the contents for this course and also developing, helping me for creating the assignments and managing it. So, I hope that in this course you have learned something which is really useful to you, and I am hopeful that all these things will be useful in the longer run in your future endeavors and also in future research. I wish you all the best, and again, if you have any queries, you are please feel free to email me and feel free to ask your questions, and I will be more than happy to answer your queries. Thank you very much, and I wish you all the best in your career. Thank you.